Weird. Okay, so this is, I couldn't make it work for a second. So this is the last part, particle strengthening. Okay, so what do we mean by particle strengthening for those non-MSE people? Really, right, the small particles of a secondary phase dispersed within the matrix, right? So these are particles that are very small compared to the grain, but larger than the dislocation, right? Right, they're clusters of atoms ranging from tens of atoms to thousands of atoms are really effective at promoting hardening, right? And we can say that the aggregate of solute atoms resists dislocation to a greater degree than isolated solute atoms in solution. And these can have a very significant effect even when the volume fractions are pretty low, like less than 10%. If your particles get much larger than this, the effect decreases because the separation between the particles for a given volume fraction goes down, right? So remember, our degree of strengthening depends on the that L prime in the denominator, right? So if our obstacles get very far apart, then this effect goes down, right? And so the degree of strengthening depends on the particle size, the volume fraction, the number of particles that we have, the particle shape, the spacing between the particles, and the nature of the interface between the particle and the matrix. All right, we're going to simply talk about spherical particles only, right? Because they have a more, we're only interested in the fundamentals really, right? But non-spherical particles can have a larger effect, but they're much more difficult to describe quantitatively, right? And really, we only care about the understanding the fundamentals. Okay, so the first thing is boundary coherency, right? So here we have an interphase boundary between phase alpha and phase beta, right? So here we have a coherent or ordered boundary, right? And there's a one-to-one matchup between the atoms, right? And because we have different parameters here, there's a coherency strain associated with this type of boundary. These atoms have a tensile strain associated with them. These atoms will have a compressive strain or stress associated with them. Okay? Or we could have a completely disordered interface where there is no pattern, there's no coherency strain because the atoms just don't match up. This is a really complicated structure, right? So dislocations can pass pretty easily through here, not so easily through here, right? And then we have a third type, right, where this is a coherent boundary but the coherency strains would be too large. But we can remove a lot of those coherency strains by having a periodic array, in this case of edge dislocations, right? That helps help remove those coherency strains. Okay, so coherent boundaries, and when they're small particles, the dislocation can cut through, right? And they'll have a sigma critical greater than 0, right? This is the Fe critical. The angle, the dislocation has to bow around. I'm making a hand gesture that you can't see. The particle in order to cut through. When the particles are large, or when you have a strongly disordered interface, the dislocations will bow around the particles completely, rather than cut through them. Okay, so let's look at the effect of interface coherency, right? So the coherency, precipitate coherency is analogous to size effects in solid solution strengthening. There's an atomic volume mismatch between the precipitate and the interface, right? That's right. So there's a internal lattice strain. Anytime you have a lattice strain, we have a stress field around here that can interact with the dislocations. So it's very difficult to treat this rigorously. And again, in my point of view, working through a really complicated derivation doesn't gain you much. What is important to understand is that you have a fairly strong effect here, right? What's it depend on? Well, the radius of the particle, the volume fraction of the particle, this parameter, this dimensionless parameter epsilon coherency, which is a difference in the lattice, which relates to the lattice parameter mismatch of the sizes. So if you just understand what goes into the term is much more important to me than if you're able to work out through the derivation of this. Okay, so that's coherency, right? That was analogous to size. We also have modulus, right? The dislocation, the precipitate has a different elastic stiffness than the matrix around it, right? So the line tension of the dislocation is going to be altered when it goes through, right? And for right now, we're just going to simplify the treatment by saying that the Berger's vector is the same in both. Okay? But you can imagine the biggest energy change is going to happen when the dislocation is halfway through the particle, right? When the greatest area of the dislocation is in the matrix, that's where the energy change is going to be different, right? And the force is going to be proportional to the gradient of the energy, right? So we're going to introduce this epsilon term, which is the difference in shear modulus between the particle and the matrix. Right? So it's the Berger's vector squared times this proportional difference in the shear moduli. Okay, but in reality, the dislocation doesn't stay straight. The dislocation is bent, right? So the dislocation starts to bow around this, right? And then it cuts through. So it's really an arc. So the greatest area of dislocation line is slightly less than the radius of the particle. And if you correct for that, you end up with a slightly different form, right? You have this should be capital G, shear modulus, Berger's vector, radius of the particle, and this, right? But those are the things that go into it, right? It makes sense. The modulus, the size, the Berger's vector, the shear modulus, right? All those go in. Just understand the physical mechanism of where this comes from. It has to do with that we're altering the line tension as we go through because now we have a modulus mismatch. Okay. Right, that was the force. Right, we want to make this a shear stress. Right, so we're going to divide the force by the distance, effective distance between, times the Berger's vector. And we end up with a form here. It's a really approximate result, right? I'm not going to, you can work through a more rigorous analysis and come up with a form where you've got a constant out here that's about 1/10, the shear modulus. This is the relative change in moduli, volume fraction, radius of the particle, and the Berger's vector, all square rooted. Right, and notice that this is a very similar expression to the coherency strengthening. Okay? There's other types of particle effects we can get. When you cut through a particle, right? Dislocations here, it's bowed around, it cuts in, it creates a step on the surface of this previously spherical particle, right? And when it cuts out, it creates another step here. This is new surface area being created. So there's there's surface energy associated with this surface, and it takes additional force, right? Your dislocation has to provide energy in the form of mechanical force to create this surface, right? And this is generally a very weak effect, except when the particles are very small. You can imagine that this is a big contribution to the total energy of the particle when it's only a couple tens of atoms or hundreds of atoms, versus when it's thousands or tens of thousands of atoms, right? And it has a very, very similar form before, right? This is an epsilon parameter, which gives you the relative change of surface energy, right? And this same term, this FR by B to the square root. Right? Okay, and then we have the last strengthening mechanism for particles is the order strengthening. Right, so these precipitates are secondary phases for the most part. A lot of them are ordered structures, like the gamma prime in superalloys. We can imagine here we have a binary structure with composition AB, right? And it's in an ordered lattice A, B, A, B, A, B, right? Where A is completely surrounded by B and B is completely surrounded by A, kind of like a rock salt type structure, right? Now this dislocation is going to shear everything over, right? So as it goes through, it's going to create a mismatch. Right now, this A is not surrounded by B's anymore. Now it has an A down here. Right? And this is an antiphase boundary. Right? And of course, there's an energy associated with that. Right? And so you have to do work to do this. Now, if another dislocation comes through here and shears it again, it's going to reverse it and bring it back. Right? So that removes the energy, right? So that dislocation will go through much more easily than the first dislocation. Okay, and so that's order strengthening in a nutshell, right? And it's proportional to the antiphase boundary energy, basically to the 3/2 power. Right? And again, we're not going to derive it. It's more important just to understand the physical basis of where it comes from. Okay? So that was for particles that we can cut through. Well, what about particles that we can't? Right? So here we're looking down. We have this this particle separation. The channel width between these two particles is the distance minus 2 times the radius. Right? So the dislocation hits, it bows around, it keeps bowing around until these two dislocations meet up. Right? And basically bypass, and you're left with 2 dislocation loops around your particle, right? These dislocations come back together and meet up, right? Remember that the dislocation, an easy way to think about how these things meet up, right, is your dislocation is a line between the slipped region and the unslipped region. So back here is slipped, out front hasn't slipped. This keeps bowing outward. Eventually, and this moves in and this moves in, eventually the two slipped regions meet, leaving behind a little wake of unslipped region. So you're left with a dislocation loop around the obstacle, right? Where now this whole region has slipped, and this little region in here has not. And this this dislocation, this interface, right, now continues to move on. So sometimes it's easier to think of dislocations as boundaries rather than as a discrete defect kind of thing. And now our channel separation has gotten smaller, right? Now, because our effective particle size is not just the particle itself, but it's this whole unslipped region, right? Because the dislocation, another dislocation, is going to interact with this one, right? Either positively or negatively, right? But in plastic deformation, we keep shearing the same way, so you would expect another dislocation of the same sense to come through here. And so there'll be a negative repulsion between that dislocation and this dislocation. So the channel width that it has to go through becomes effectively smaller, right? And if this becomes this denominator becomes smaller because our L prime, right, is now smaller. So our tau, our stress that we need to bypass, becomes higher. Okay, and so we have this overall effects, right? So we have as the particles get bigger, right? When the particles are small, they tend to be cut. When the particles are big, they tend to bow around them. So you can see here how difficult it is to cut gets smaller as the particle gets larger, right? And the how easy it is to bow around gets harder as the particle gets larger, right? So the ideal size is right where these meet, right? When you're getting the most strengthening when cutting and bowing are effectively equal in strength, right? Because if your particle is right, it's going to do whatever is easier, right? So the way to get the most mileage is when those two strengths are exactly the same, right? So here we can see an example of this, right? So this is precipitate size, right? And this is hardening, right? There's a maximum size before it gets smaller, right? And this is due to a couple of things, right? Primarily, we see this as the particles get larger. If we stick at a constant volume fraction, the separation between them gets much larger, right? So our denominator, that L prime, gets larger, so our effect goes away. Right? So these are the things we have to think about, right? You want your particles to be ideally at the right size so that cutting and bowing are equal, and you want to have the right volume fraction of particles so that your effective separation is good. Right? And that wraps it up, and we'll do some exercises and stuff in class.